You are watching this video because you are getting ready to do an experiment, do a lab. And in the process of doing this lab, you are going to recreate history. That's right, recreate history. There is perhaps no more influential figure historically in the development of our understanding of gravity than Galileo Galilei. Despite having a pretty awkward name, he was a remarkable guy. And he did this experiment in the 1600s, in the early 1600s. He did a version of this experiment to find the acceleration due to gravity, which he had figured was a constant near the surface of the Earth. And you're gonna repeat that experiment. I want you to come to class next time with a pre-lab written so that you can kind of hit the ground running when you do this lab. But in order to do that, I'm going to have to give you some background. And so thanks for watching this video. That's the whole point of the video. If you do not have a handout, which probably looks like this, then you should go to Teams and you should find the AP lab for Galileo's inclined plane and print it out and follow along with me as I talk you through it. This is good stuff. Whoever wrote this was a genius. Okay. At the beginning, this is a ramp. It's a dynamics cart ramp. It's very exciting. It's a piece of aluminum. There's a little block on one end. There are some feet on it, on each end, to help you level it on the table both ways. Those feet screw up and down and they help you level the cart. The whole idea here is we're going to roll some stuff down the ramp like a ball. Galileo had a wooden ramp, and down that ramp he would roll balls that he had made out of wood or heavier like marble, stone. And they could actually make spheres pretty well in those days, which is a little amazing to me. But he would tilt up the ramp and he would roll the ball down the ramp. And he would time how long it took the ball to roll down the ramp. Now, that seems a little strange. Why would we do that? Well, let's think about that. First of all, we're not going to use a sphere. We're going to use a very low friction cart. And if you open your little box that you'll get with this lab, there are two carts in it. One is gray, and one is green, blue, green. I don't know what color this is. The one you want is the blue-green one. You can leave the gray one in the box. And I want you to think about this. If I set this blue-gray one on the ramp, and the ramp is sitting horizontally, think closely about this. What will the cart do? Will it be stationary or will it roll on the ramp? Think carefully. Don't hurt yourself, but think deeply. If the ramp is horizontal, what will the cart do if you set it on the ramp? That's right, it won't move. So the acceleration of that cart is 0 if the ramp is horizontal. Now, of course, if the ramp is not horizontal, let's say we block it up with something, some paper. And I set the ramp on it. No, I set the cart on it. And I let go. What do we expect it to do? It's going to roll down the ramp. Does its speed change as it rolls down the ramp? Or does its speed stay constant? Well, it starts at rest and it finishes not at rest. So I'm going to guess you agree with me that this thing is accelerating down the ramp. Does it accelerate at the same rate it would accelerate if I dropped it from that same height? For example, if I take this pen and I start it at the same height, but I drop the pen straight down, will it get to the bottom of the ramp, will it get to the tabletop faster or slower than the cart itself? Make a prediction. Here we go. This is a bold prediction. 1, 2, 3. What do you know? The pen won. We know the pen accelerates at 9.8 meters per second every second. The cart does not. Why is that? Well, if I increase the ramp angle, what does the cart's acceleration do? Hey, it accelerates. In fact, if I put the cart ramp like this, what would the cart's acceleration do? Well, I think you see, it goes straight down the ramp. Didn't mean to have that written on the board. So, if you ponder this, if we were to graph a relationship between, say, the ramp angle and the cart acceleration, what would that graph look like? Well, if the angle is 0, the cart doesn't accelerate at all. If the angle is 90 degrees, the cart's acceleration gets to a maximum, doesn't it? And in fact, we know what that maximum is. It's 9.8 meters per second squared. So that's where it starts. That's where it ends. If the ramp has angles smaller than 90 degrees, I think you agree that the cart's acceleration is smaller. I guess the question is, if this is the start of the relationship, that's the end. What does it do in between? Is it linear? Is it quadratic? Well, I suspect that it's linear. I suspect that it looks like that. In Galileo's day, he didn't have sophisticated timekeeping devices. He didn't have stopwatches. All he had were pendulums and hourglasses and things called water clocks, where you'd have a big bucket of water and a little tube that came out of the bucket of water, or just a smaller bucket to catch water that came out of the big bucket. You put a little hole in the bottom of the bucket and you would say, "Go!" And if you were Galileo, your assistant would release the water valve and water would drip from the big bucket into the little bucket. And they knew how much weight of water would go from the big bucket to the little bucket in a certain amount of time. So they could weigh the small bucket, and based on how much water weight there was in it, they knew how much time had passed. And that was called a water clock. And Galileo used water clocks to time stuff. Now, you can imagine using a water clock to time the dropping of this ball would be a little silly. It happens way too quickly. Galileo couldn't measure things as they fell straight down. They couldn't measure the time accurately enough. But he could build long ramps and measure this kind of time very accurately. And the ramps that Galileo built were several times longer than this. They would go clear across the room. And so he would time elapsed times that were on the order of several seconds, 9, 10, 11, 12, 15 seconds even. And by doing so, he could measure time quite accurately. The problem is, he couldn't drop stuff straight down and measure its time. He had to slow the whole gravity thing down. So what he did is built a ramp and used very small ramp angles, and measured very small cart accelerations in the process. So he was living in this part of the graph, way down here. And that's what we're going to do. That's what we're going to do as well. The question, of course, is how do you figure out the relationship between these small accelerations and the acceleration due to gravity? That is a mystery. Or at least it is now. But it won't be by the time you're done with this lab. Okay, so the point is, Galileo's inclined plane lab, we will use small cart accelerations at a variety of ramp angles to determine the acceleration due to gravity. So we won't measure little g directly, we'll measure it indirectly by measuring the acceleration of a cart that's rolling down a ramp. Yay! How do we do that? Okay, well, first of all, we're going to use a lab quest. And we're going to use some other stuff that's in this cool little box. This thing. This is a motion encoder receiver. And it turns out that this and the green cart can talk to each other. The green cart has a little button on the end that you can push and it will glow blue. That means I've turned the cart on. If I set the cart on the track, you'll see there are little stripes on the track. They look kind of like a barcode. These stripes are read by a sensor in the bottom of the cart, and as the cart passes the stripes, it can tell how fast it's passing the stripes, and it can measure not only location, but also determine speed, and so on. So all we have to do is plug in this, which talks to the LabQuest, and relays information from the cart to the LabQuest. We got to plug this in to the LabQuest. It's tempting to plug it into the end where there are some ports. If you try to do that, it doesn't fit. I'm coming around. The LabQuest has those ports on the end. This cable looks like it should fit, but it does not. So do not force it. If you try really hard, you can probably get it to go in there, but you will break something in the process. These LabQuests have a secret panel. On one side, there are these little rubber doohickeys that pull out, and they expose additional little ports under there. These are the digital ports, and those connectors plug in just fine to the digital ports. So we plug that in there. You'll notice that the ramp has this stripy pattern. The stripy does not go down the middle of the ramp. This also has a stripy pattern. And the cart, right there, also has a stripy. To set this up right, you got to line up all the stripies. If I put the cart on the track this way, the stripy on the cart is toward the bottom, and the stripy on the ramp is toward the top. They do not line up. If I turn the cart around, the stripy on the cart and the stripy on the ramp line up. Likewise, if I take this doohickey and I attach it. By the way, this slides on the end of the ramp like that. Slides on. If I slide it on that way, the stripy don't liney uppy. No liney, no uppy. No stripy liney uppy. That's bad. So, try it on the other end. Now, stripy liney uppy, we're happy. We need the encoder to line up with the stripes. We need the cart to line up with the stripes. And if we get it right, the happy news is the cart will talk to the LabQuest, and the LabQuest will talk to you, not literally, and it'll all be happy, and we'll see this kind of thing. Whoa. It's all right. Almost. That upside down. What? Huh. Uh-oh. Well, That's convenient. Maybe the video will correct itself when it post-processes, but it looks to me like this is backwards. These letters are backwards in the video, which is unfortunate. To me, they look just fine, but to you, they may appear backwards. That's unfortunate. Neat. Anywho, I guess you'll just have to read them backwards. It says 1160 right now, 0.116 meters. If I move the cart, that changes. The position of the cart is what's being reported here. And if I hit go on the LabQuest, and I give the cart a push, graphs are produced of position versus time and velocity versus time. So what? How are those useful to us? Well, remember that the purpose of this lab is to measure the acceleration of the cart. How is acceleration related to a position time graph? Well, you're right. It's not easily anyway. How is the acceleration of the cart related to the velocity graph? You're right. It's slope. So, if I could display just one graph, I would want to display the velocity graph. In fact, I don't think the position graph does me any good at all. The good news is I can display just one graph, and I think you should too in this lab. I hope you can see this. Huh. You can sort of see that. Okay. I will narrate. What I'm going to do is tap the graph menu. And this says show graph. I want to show currently all graphs, but I want to show just the second graph. And when I do that, I can see just the velocity versus time graph. Okay, so that's how I can display just one graph. If I were to, you know what? Always put this end block on the end of the track so that the cart can't just roll off the end of the track. You do that by loosening this screw. You don't have to take it all the way off. You just loosen it. You can slide the end block on and tighten it down, and that end block is secure. And now you can actually run the cart into that end block and nothing bad happens. I would encourage you to catch the cart as you do these. Don't just let it run into it. All right, if I hit go, well, another thing. I would like my zero position to be at the top of the ramp. If I want to change anything about the LabQuest output, I just tap on the output and see what happens. There is a zero option right there, and I can zero that output. Now it is zero at the top of the ramp, and it becomes more positive as it rolls down the ramp. That seems like a good idea to me. My positive direction is down the ramp. That's awfully linear. That's a velocity versus time graph. The slope of that line is acceleration. And the LabQuest lets me find a linear region, highlight it. My menu options are File, Graph, or Analyze. I'm going to select Analyze. There are lots of options here. Statistics is a nice option. I want the slope of that line. I'm sorry. Curve fit is an even better option. I want the slope of the line, curve fit, velocity, What kind of fit do I want? I want a linear fit. And these values say y equals mx plus b. Here's my m value. That is my acceleration, 0.1168. My y-intercept value I don't think I care about. I have just measured the acceleration of the cart when it rolled down that ramp. Furthermore, the correlation is 0.9976. Remember, a perfect correlation is 1, and I'm awfully close to 1. That's a pretty dandy value. I could repeat that a couple times, get some data that I can trust. And I have just generated a data point that might form the basis of a graph for me. I have a small angle, I have a small cart acceleration, and I'm building the beginnings of a graph. That's the basics of what we're after here. To build a graph that relates cart acceleration to the configuration of the ramp. Okay. I need to test something.